Hi, I'm Zor. Welcome to Unizor Education. We continue talking about curves on the plane, which we generally regard as the curves of the second order. Now, the previous lecture was about ellipse, and why is this a curve of the second order? Well, if you remember, in Cartesian coordinates, the equation which basically characterizes points x and y to lie on ellipse was this one, which is the second order x squared and y squared. Now, today we will talk about hyperbola, and just to make things very, very quick, I would say, the only thing which we need is to change the sign to minus. And that would be an equation which characterizes hyperbola. But let's do it step by step. First of all, we need to define what is hyperbola. Well, again, back to ellipse, you remember that we had two foci, two focal points, f1 and f2. We also have something which we call major axis. So A is semi-major axis. And for ellipse, the characteristic of the ellipse was sum of the distances from point on the ellipse to 2 foci should be equal to 2a. Okay, now, as far as the definition of the hyperbola, it's very simple. We just change this to minus, and that's it. So the difference between distances should be equal to 2a. Okay, another very important thing was distance between f1 and f2 is 2c. So c is called basically a focal distance. And what's important is c should be greater than a. And here is why. If you have system of Cartesian coordinates here, we're talking about Cartesian right now. Now, so this is equal to c. This is equal to c, right? Well, the coordinate of this point is minus c0, coordinate of this is c0. These are focal points, foci. Now, a should be smaller than c, so a should be somewhere here. And this is minus a, right? Okay, now, the point, let's call it a and b. So 0a is equal to a, 0f1 is equal to c, and the same as OB, the same as OF1, F2. I'm talking about distances, not coordinates. So this distance is c, but the smaller from origin to point A, the distance would be a, which is c is greater than a. Now, let's talk about point A, let's say. From point A to this particular focus, distance is c minus a, right? So AF1 is equal to c minus a. Again, c is greater than a, so a is closer to the origin. Now, from the same point A to F2, the distance would be what? A and c. A plus c. Okay, so the difference between them, the bigger difference is AF2. So AF2 minus AF1 is equal to a plus c minus c plus a, so it's 2a. So point A lies on the hyperbola. Now, let's talk about B. BF1, B to F1 is C and A. C and A. From B to F2, well, that's C minus A. And if I will subtract them, BF1, which is greater, minus BF2, C plus A minus C plus A, again to A. So as we see, points A and B belong to our hyperbola. And AB, by the way, that's the major axis, remember? Because the distance between them is 2A. Okay, so how the hyperbola behaves actually? Well, we know we can start, let's say, from point B. What happens next? Well, from point B, we can go a little bit up, but in such a way that the difference from the point, let's say it's point P, somewhere here, in such a way that the difference between the distances is exactly the same. Now, what if we will move vertically up? What happens with the distance? Well, let's see it this way. Okay, this is my point F1, F2. Now this is my point B. So for point B, we know that the difference between these distances is 2A. What if we will go vertically up? Well, what's the difference between these two guys? Well, whenever you are measuring distance between these two versus difference between these two, so PF1 minus PF2, compare it with BF1 minus BF2. The higher you are, the smaller distance, the smaller difference between PF1 and PF2 becomes. And as it goes to infinity, the difference would be actually closer and closer to 0. Now, so we cannot go up. To maintain the same distance, we have to do a little bit this way. And that's basically is the shape of hyperbola. It goes this way. And it goes in such a way that it would be at some point asymptotically closer and closer to these lines, because only if you will go along these lines your difference would be more or less the same. But in this case it's just asymptotically closer and closer to these lines. Now similarly, from the point A, if you would like to basically draw a hyperbola, it would be closer and closer to these lines asymptotically. So this one is the difference between PF1 minus PF2 is equal to 2A, but this one is PF2 minus PF1 is equal to A. So the if we are talking about the absolute value of this, then it's two different branches. Okay, so let's talk some coordinate space. So we will introduce this type of Cartesian system of coordinates, and let's see what our equation might actually look like in Cartesian system. So difference from P to F1. What is this difference? Well, coordinates of this point is xy, coordinates of this point is minus c0. So it would be x plus c square plus y square and square root, right? Difference to point B would be square root of x minus c plus y square. And if we will subtract from one another, we should get 2a. Well, that's it. That's the equation in Cartesian coordinates. Problem is, well, it's kind of ugly. These square roots, nobody likes them, obviously. But as in case of ellipse, there are certain transformations of this particular equation to a simpler form. In the notes for this lecture, which you can find on Unizor.com, you go to Math Plus for all, choose geometry and choose hyperbola in the menus. You will see the full derivation, but it's kind of straightforward. So what you do is you move one of the square roots to the right, square both sides, at least you get rid of one square root, then again you are isolating square root and into one side of the equation and everything else on another, square it again, cancel whatever is necessary, and as a result you will get this. Minus, that's important, where b square is equal to c square minus a square. C is greater than a, so b is positive. B is called, by the way, semi-minor abscess. In case of ellipse we had geometrical representation. The difference between these points is major and the difference between these points is minor. In case of hyperbola, we do have the so these are Foci, this is A and this is B. So difference between these 2 points, the distance between these 2 points is to A. So this is a major axis. As far as the B, you just have to basically be satisfied with just an algebraic expression. I cannot draw what is exactly the B in this particular case. I mean, there is a way to do it, but it's kind of complicated and not very interesting. Okay, so I'm completely skipping all these calculations on the board because I put everything in writing onto the Unizor.com. Again, you go to the course called Math Plus for all. You choose geometry as a major subject of this course, and you choose hyperbola on the next menu level. And everything is in there. Okay, however, I do want to do something in polar coordinates, exactly the same way as I did with ellipse. I skipped all the Cartesian because it's kind of boring, but the polar coordinates are kind of simpler to arrive to. So let's talk about polar. Now, as in case with the ellipse, I will choose the polar coordinates. So this is A, this is C, this is point A, this is point F2, and I will choose the polar coordinates with origin at the focal point, at the focus of hyperbola. Why? Because again, we have a point which is characterized by radius from the origin and angle, right? So the length between point P and F2 is already R, because F2 is an origin of polar coordinates. Now this is angle theta. So at least I have a little bit simpler expression because the distance to one of the foci is very simple. It's just r. Now this is minus a and this is minus c. This distance is more complicated. So from P to F1 is equal to R, and from P to F2, this is F2, this is B, from P to F2 is slightly more complicated. However, you can always consider this triangle F2, P, F1. So what do we know about this triangle? We know this side, which is equal to 2c, right? C, difference, the distance between two foci. We know this angle, which means we know this angle. So its angle would be pi minus theta, right? So we have two sides, one is r, another is 2c, and we have an angle between them. So there is a law of cosine which we can use, exactly the same as, by the way, in case of ellipse. So the square of the opposite side would be equal to sum of the squares minus 2 times one side times another side times cosine between them. So it's 2 times r times 2c times cosine of pi minus theta, right? Okay, great. So now obviously we can have that the pf2 square is equal to r square plus 4c square plus, you see, cosine of pi minus theta is minus cosine of theta, if you remember trigonometry. If you don't, try to recall it. So it's 4, 2 and 2, 4 rc cosine theta. Okay, great. So now what we can do is just put that simple characteristic property of the hyperbola, that the difference between pf1 and pf2 is equal to 2a. So square root of r square plus 4c square plus 4 rc cosine theta square root minus, so this is pf2, minus distance to another focus, which is minus r, is equal to 2a. That's it. So that's my equation, and all I have to do is simplify it. And this is a very simple exercise. So you put r to the right, and you square both sides, so it's much faster than in case of Cartesian coordinates. There we have to square twice to get rid of one square root and then another. Here it's just once. So r square plus 4c square plus 4rc cosine theta equals 4a square plus 4ar plus r square. All right? R square plus c square plus sc. Yeah, looks like it. Okay, what can we do? Well, we can get rid of r square on both sides. We can get rid of 4. They're all multiple of 4. And all we have to do is connect r to one side and everything else to another side. So we will put this r to the right and a squared to the left. So c square minus a square equals, r can be taken out, a minus c cosine theta. Okay. Okay. Then what we usually do in case of, and we did it for ellipses, we introduce eccentricity, which is c over a. Okay. From which case we will get a square e square minus a square is equal to r a minus a e cosine theta, right? So c is equal to a times eccentricity. Now we can divide both sides by a. You see, a. So we will have a e square minus 1 is equal to r 1 minus e cosine theta, from which r is equal to a e square minus 1 divided by 1 minus e cosine theta. That's the final. Now let's think about it right now. First of all, it's very similar to equation which we had for ellipse. For ellipse we had r is equal to a1 minus e squared divided by 1 minus cosine e cosine theta. Very similar, just the sign of this is different. However, what was very important actually, that in case of ellipse we had this condition. In case of hyperbola we have this condition. So for ellipse, for any theta, we had denominator positive because cosine is less than 1 or equal to 1 and e is less than 1, so it's always positive. And the numerator is always positive because it's 1 minus e squared and e is less than 1. Well, and greater than 0, obviously. We're talking about positive eccentricity. Now, in this case, situation is much more complex because there are certain angles, theta, for which the denominator would be negative, and there are certain theta where it will be positive. Numerator is always positive. So our condition for existence of r is supposed to be positive, right? Is 1 greater than e cosine theta, or cosine theta should be less than 1 over e. 1 over e is a divided by c. A is smaller, c is greater. So whenever this particular condition is good, then we will have positive. When it's not, well, sorry about that. Now, for example, if theta is equal to 0, cosine of theta is equal to 1, and this is definitely not, this is not true. A is smaller than c, so the whole thing is less than 1, and cosine is greater than 1, is equal to 1. So graphically, if this is your hyperbola, this is your focus. When is theta is equal to 0, it's this direction. This is the major base polar axis, and angle is equal to 0. So we don't meet any hyperbola point along this line. However, if you will do theta is equal to pi, which is that direction, what you will have, cosine of theta is equal to cosine of pi is minus 1. If it's minus 1, then you have r is equal to a e square minus 1 divided by 1. Now, cosine is minus 1, so 1 plus e, or e plus 1, doesn't matter. So it's e square minus 1 divided by e plus 1, that's e minus 1. So it's e minus 1, that's a times e is c over a, right, minus 1, so it's c minus a. And indeed, this is c, this is a, so c minus a is this distance, and that's exactly where we will meet our hyperbola if we will go to the left, right, at angle theta is equal to pi. So basically, again, as I said, this is a condition. You can transform this condition into arc cosine if you wish. So that would be arc cosine should be, okay, if it's from minus arc, theta, arc cosine of what? 1 over e, so AC, a divided by c. If theta is in these boundaries, so actually if this is the if you remember, we're talking about asymptotically closing this curve, closing to these lines. So whenever you have parallel lines here, so within this angle, which is from minus arc cosine of a over c to plus arc cosine, you will not meet any point of the hyperbola. So if this is parallel to asymptotes, so within this angle you will not meet. As long as you are outside of this angle, so if theta is greater than arc cosine, or, which is this way, or less than minus arc cosine of a over c, then you will hit some point, and the r would be some value, whatever the distance from focus to that particular point is. So this is kind of analysis of the shape, how this particular thing looks like. But what's interesting is that the equation in polar coordinates is almost the same, as I was saying, as equation for ellipse in polar coordinates. And that would be very interesting and important when in the physics course we will talk about gravitation. Because the problem is that if this is your central mass, which is the source of gravitation field, and you have some kind of an object which is going at some speed from some initial point in this field, if this speed is not very high and the distance is really relatively close, it will actually go to the ellipse. But if some parameters would be different, for example, speed would be very, very high, it will curve, but it will still go away along a hyperbola. So that's what we will be doing in physics, and that's basically why I decided to spend some time for all these curves, ellipse and hyperbola, and parabola will be the next actual lecture. I decided to spend some time, and especially in the polar coordinates. What's so important about polar coordinates? Well, in case of gravitation, we don't have any coordinate system in the field. All we have is one point where the source of gravitation actually is located. So, and that would be the focal point, that would be the focus of the curve, whether it's an ellipse or hyperbola, whatever it is. And that's why it is important to have a polar system of coordinates which is originated at the only point which we know. We don't have any other points, and have as a radius actually. So angle and the radius would be our coordinates. Because in case of Cartesian system, as you saw, I know A beforehand. I defined hyperbola or ellipse using C and A, the focal distance, and major axis, semi-major axis. In case of real world, in case of physics of gravitational field, I don't have any parameters. I have position and the speed, and I have parameters of the source of gravitational field, mass. That's it. So I had to resort to the system of coordinates which is somehow related only to these parameters which I have. Okie doke, that's it. I suggest you to read the notes for this lecture. Especially, I think it will be very educational if you will derive the Cartesian coordinates formula yourself. Well, if you don't, you don't, but you can always read it in unizor.com. Also on the same website, unizor.com, you can find many other courses like Maths for Teens, Physics for Teens, and others, Relativity. So that's it. I suggest you to do this exercise, and that's it. Good luck. Thank you very much.